This is Mrs. O'Neill for AP Chemistry, Chapter 11, Section 2, Part 5, Hydrogen Bond Forces. Now, this is where I'm not a big fan of how they classify or label this particular IMF because they call it a hydrogen bond. However, it is not a hydrogen bond. A bond to me is between two atoms that form a molecule or that one unit. However, this is the hydrogen bond in quotes. It's the force of attraction of hydrogen atom in one molecule and there's only three other elements that it would be attached to in another molecule. That attractive force from two different molecules, or I should say two of the same molecules but attracted together, would be considered this hydrogen bond. So not in favor of how they actually classify or label this particular IMF. So it is the third of the four major IMFs. And again, I'm doing it in strength. So their dispersion or LD forces were the weakest. Dipole were a little bit stronger. And now these hydrogen bondings. Now this is what's tricky about hydrogen bonding. Number one, it's not a bond. And number two, they're polar molecules. This hydrogen bond is a polar molecule, but it's in a different classification because it's stronger than a normal dipole. So when we're talking about dipole IMFs, we're talking about two polar molecules and how they have that positive negative in their molecule. So when they come close together to each other, they have that attractive force. Well, hydrogen bonding, think about water, is very, very similar. We know that water is polar, but it is so polar that it's almost ionic to the point where it's going to be even stronger. And that's why it's in a different category. So pause the video, fill in the blanks, and then play to hear my words. Again, read as you write. So this attractive force is so strong. It's really another form of dipole attraction, but it's stronger, and that's why it's put into its own classification. So when hydrogen is attached to either nitrogen, oxygen, or fluorine, now we're going to put it into this hydrogen, quote, bonding category, because these three guys have high electronegativity, so their strength of attraction to draw those electrons to itself is so strong that it's almost ionic, and that's where we get that from. Also, these atoms are really small, right? So the bond length between that hydrogen and NOF is going to be very short. And remember, we talked about the shorter the bond length, the stronger that force of attraction is. So I bring the periodic table to your attention because look at the location of NOF. So if we want to remember, hydrogen bonding really deals with nitrogen, oxygen, and fluorine. Remember, fluorine has the highest electronegativity where it is, right? That's the trend. And it is the smallest atom, right? One of the smallest atoms compared to like hydrogen. So we have really small hydrogen with really electronegative elements, makes it a really strong force, and this is why it's put into its own classification. Just like before, hydrogen bonding then can also experience dipole and LD forces. So why is water so strong? So this is different versions or different pictorials of water that chemists like to put together. But the major thing is here, if we look at how hydrogen is structured, right, it's always based off of structure. Structure, again, is very important. We get lots of information from the molecule's structure more than anything else. We're going to now focus on the two unshared pairs of electron around the central atom. And when I mean central, it might not always be the center of the molecule, but it's inside. It's not on the outside. So we're talking about the oxygen that's inside this water molecule and the fact that it has two non-pairs of electrons. So that's going to be really important to make it very polar. So when we're comparing three compounds, let's look at H2O, NH3 and CH4. Well, this guy, again, has two unpaired shares of electrons. So first of all, if there's hydrogen bonding going to occur, it's going to be between this oxygen of this water molecule and a hydrogen from another water molecule floating around. So it's oxygen of one, and it's the central, and the hydrogen of another that's also attached to that oxygen. And because of the two lone pairs of electrons, it is the strong, very strong hydrogen bonding. Well, let's look at this guy. This is ammonia. So again, we have one unpaired shares of electrons. So we have hydrogen bonded to nitrogen. And if we have another NH3 floating around, this nitrogen would have that hydrogen bond to another hydrogen from another ammonia. So that would be that hydrogen bond between nitrogen and hydrogen. So again, strong hydrogen bonding. But if we look at CH4, first of all, it's carbon. So carbon does not have any hydrogen bonding associated with it, as well as there's no pairs of electrons to make that force of attraction. So this one doesn't even have any hydrogen bonding, so it's not strong at all. So I went from the strongest to middle of the road strong, and then not strong at all. So hopefully that makes sense in comparing how strong this hydrogen bonding really is. So if we look at these four pictures, we have the blue, the red, the green, and let's say the purple. Blue, red, green, purple. Pause the video and see if you can decide which one really has hydrogen bonding. Only one of these has hydrogen bonding. And of course, the Y. Hopefully this makes sense. Your blue box, the F, is not the central atom. Remember I said the F, or wherever the hydrogen bonding is going to occur, has to be like on the inside, not on the outskirts of the structure. The red box, again, the oxygen there, really doesn't have any unpaired shares of electrons. You know what? Maybe it does. I apologize. There probably is, right? Because 1, 2, 3, 4, 5, 6, 7, 8. There is two unshared pairs of electrons. However, again, it's not the central atom. The green box, same thing, yeah, because this C-double-O is the same as this C-double-O, so it's just that it's the outskirts, it's not on the inside. So if we look at this molecule, what's different here? Well, first of all, nitrogen is one of the hydrogen bonding elements, NOF, right, nitrogen. It is a central, right, it's inside, and it's also attached to a hydrogen, and it's going to have an unpaired share of electrons. So we have those, so the answer is obviously this purple, and there's the Y. So again, pause the video, make sure you're understanding this information. So now let's look at this methylamine. Again, pause the information, read over this, make sure you're understanding the looks of the structure, and I do believe in your notes you should draw this. And what are you drawing? You're making sure that you're understanding that this is a pot, right? A pot, we have lots of these molecules, methylamine molecules in there, and where's the hydrogen going to occur? Well, this hydrogen is attached to this nitrogen, and this nitrogen is attached to these hydrogens. That's where the hydrogen bond's going to be. So what's different with this guy? Why is this not correct? Because this hydrogen is attached to the carbon, and carbon does not is not part of that hydrogen bonding classification. So again, it's the nitrogen of one and the hydrogen of another, but you got to look at what that hydrogen is also attached to. So this would be the correct labeling of hydrogen bonds. So again, pause and make sure you draw something that you're understanding this information. So hydrogen bonding also affects boiling point, and the easiest way to understand this is by this graph. Okay, so we have a boiling point, and we're going to graph boiling points of group 14 attached to hydrogen. So we have CH4, which is methane, silicon, germanium, and tin with hydrogen. So these are all they're all tetrahedral. They all do not have a pair of electrons. There's no hydrogen bonding going, right? Hydrogen is not with NO or F. So this actually should make sense. As we increase the molar mass, we're increasing the size of the atoms, and we are it should be increasing in strength, right? So increasing size, increasing molar mass, increases the boiling points, because this guy would be more polarizable. Even though they're all non-polar molecules, this guy would be more polarizable because it's the bigger guy, so he would be a little stronger. So Very, very weak IMF forces there. If we look at group 15, we get something slightly different. So these are going to be more polar, right? These are going to be dipole molecules because they all, again, have that one pair of electrons. But this guy's kind of weird, right? He doesn't kind of fit the bill. These guys do. These guys were increasing molar mass, we're increasing the size of the molecules, we're increasing polarizability, so we're increasing the strength of boiling points. But this guy's really high. Wonder why. So let's do group 16. Holy patooties. So again, water really, really high. We know that he boils at 100 degrees Celsius. But again, these guys are going to have all the polar molecules and have two lone pairs of electrons that are not shared. And again, this fits the trend, right? We are increasing molar mass. We are increasing the size. We are increasing polarizability. So we're increasing the boiling points because they're getting strong. But this guy is, whoo, man, is he really, really strong. And that's how we can say, oh yeah, because water is exceptionally high boiling point, we're going to put him in a different classification of hydrogen bonds with IMFs. And then again, if we do group 17, same kind of thing. He's the odd man out. He's pretty high, but these guys would follow that trend that we just talked about. So if we look at this, again, boiling point is going to increase with molar mass, but hydrogen bonding is going to account for that really, really, really high water boiling point. So again, our H with nitrogen, oxygen, and fluorine. Again, hydrogen with nitrogen, oxygen, and fluorine, the hydrogen bonding elements, proves that hydrogen bonding is really, really strong. So in your notes, again, please draw something along these lines. Draw the graph in some way, whether you want to do it by different colors like I did, just labeling the different groups, making sure that you're understanding or pointing out that hydrogen bonding IMFs are really, really strong, and that's what proves them to be in their own little category. So can you pause, read the question, and come up with an answer? So again, they all have the same molar mass, so what should we look at? Definitely the structures, right? Again, when you have similar molar masses or you have similar size, now we have to look at the structures. So here's the two structures. Now pause the video and can you give an answer? So again, hopefully that makes sense. So you have two areas where you can have hydrogen bonding, and hydrogen bonding, of course, is going to be that stronger IMF. If it's stronger, that means you have higher boiling points and all that stuff. And again, pentane here is just your normal non-polar molecule. So again, pause, read, make sure that makes sense. So how about if I give you three structures here and I ask you which one is probably going to be a solid at STP and the why. So there's your three structures. Let's think about this. Again, using that periodic table, looking at where chlorine, bromine, and iodine are, and now look at the different colors. We have chlorine as a gas, bromine as a liquid, and iodine as a solid. So what's going on here with IMFs? Well, of course, the IMFs are getting stronger because we're going from a gas to a liquid to a solid. So if we look at those diatomic molecules, same kind of thing. We have our gas molecules, our liquid molecules, and our solid molecules. But look what's happening with the IMFs. Look at what's happening to the size of those atoms. Look at what's happening to the polarizability. So again, can you answer this question? Which one of these has the strongest IMFs would probably prove that it would be the solid at STP? Well, hopefully you picked this one out, right? Because this guy, if we have a whole bunch of these in the pot, we have oxygen that's going to be the inside or central atom, and it's attached to hydrogen. So we have some hydrogen bonding going on there, meaning that we have strong IMF. So that would be the answer. All right, the end is near. I believe we have one more IMF to discuss and then a wrap-up video that kind of sums it all up and compares all four of them again. See you in class.